The next portion is rocket propulsion theory. So, in the previous session, we had seen aircraft propulsion theory, or the theory terms associated with the propulsion of aircraft. Now, the basic difference between rocket propulsion and aircraft propulsion is, like aircraft propulsion normally happens through the surface of the earth only, so always there will be air pressure and all those things, but rocket propulsion can take place in the outer space also. So there is a major difference. And the second thing is, so aircraft devices are commonly known as air breathing engines, because air is directly taken from the atmosphere and is being utilized for the actual combustion process. But here, obviously the oxygen for combustion is carried by the vehicle itself. So the basic rocket propulsion theory, what we are going to see is, we are going to see the thrust force, like F value, the specific these parameters, the equation for these parameters actually what you are going to see. Now here the mass flow rate of the propellant will be equal to, or the mass flow of the band gas at the outlet, that will be equal to m dot F, that is mass flow rate of the fuel plus mass flow rate of the oxidizer. So m dot will be equal to the weight flow rate of the propellant by G, or m dot F into, so if you are taking m dot F outside, so this will be 1 plus the oxidizer flow rate by fuel flow rate. So the total weight flow rate over time, this is not important at all. Just remember this time m dot P will be equal to m dot F plus m dot OX, or the oxidizer. So like in the previous case, we are just going to consider a rocket engine. So a control surface is being considered the outer surface. So here the major difference between aircraft propulsion and this one is, like here there is no no flow rate to the inlet of the engine, or C1 will be 0. So because air is not directly taken from the atmosphere, so C1 will be equal to 0. So the thrust is F is in the rightward direction along the movement of the vehicle, and PA, atmospheric pressure, will be acting at the control surface. So PA will be acting all around the rocket surface, and at the exit, so after expansion through the nozzle, the pressure will be PE, and velocity will be C2, which will be equal to CE. So both terms you can use, like A is the area at the exit. So these are the terms. Now the total thrust force of, if you are considering steady and one dimensional flow at the nozzle exit, the rate of change of momentum flux will be equal to, so integral over AE, that is along the this area, rho E into C square into dA. So same equation what we have followed in the previous one, rho E into C square into dA. So since it is one dimensional, you can write it as rho into C square into AE. So the flow is assumed to be one dimensional, so integral over AE into dA will be equal to AE itself. Now if you apply continuity equation, the mass flow rate of the propellant will be equal to rho E into, that is the density at the exit, into velocity at the exit, into rho A, area at the exit. So m dot P is equal to rho E into CE into AE. So the momentum thrust will be equal to m dot P into CE. So the next one is the pressure thrust. Pressure thrust is commonly the pressure at the exit, that is PE into AE. PE into, that is the pressure at the exit, into AE minus PA into AE. That's atmospheric pressure which is acting at over an area of cross section AE. Okay, so the rocket is moving in this direction. So pressure force is acting in along the surface PE into AE. And atmospheric pressure PA will be acting all over the surface of the rocket, that is PA into over a cross sectional area AE, PA into AE. So pressure force will be equal to PE minus PA into AE. So next thrust will be equal to the momentum thrust plus the pressure thrust, so m dot P into CE plus PE minus PA into AE. So you can see, like here F, the thrust force will be independent of the flight velocity. So that is a major difference, because air intake is assumed to be 0. It is not assumed to be 0, it is 0 actually. So for a given nozzle, like PE value is fixed, so thrust increases obviously with the altitude. So with PA value, so F will be equal to m dot P, that is the mass flow rate of the propellant, CE, flow velocity at the exit, plus PE minus PA into AE. So for a given design of nozzle, for a given AE value, obviously PE will be fixed. So the thrust value will depend upon PA value. Okay, so as the altitude increases, as the height increases, obviously PA will be reduced. So as the altitude increases, so this term will be reduced. So this term PE minus PA will be higher. So as PA less, as PA reduces, PE minus PA will be higher. So F value will be increased. So this graph actually shows the variation in thrust along with altitude. So the reason is like in outer space, like PA will be 0, so maximum thrust will be produced when there is no air pressure. Now if the gases through the nozzle expands into the ambient condition, so as I explained the previous case, if PE is equal to PA, that is complete expansion is happening at the exit of the nozzle, so pressure thrust will be equal to 0. So the total thrust will be equal to m dot p into, in that condition, the exit velocity is normally represented as Cj, that is effective jet velocity. So F will be equal to m dot p into Cj, or that will be equal to the weight flow rate of the propellant divided by G into Cj. Now the other terms, that is a specific impulse. So these parameters, what are the expression we have, what is mean by specific impulse, we have already seen. The thrust per unit weight flow rate of the propellant. So IS will be calculated using the equation F by W dot P, that is the weight flow rate of the propellant. So F is the net thrust produced. So combining equation 9 and 10, these two equations, so IS will be equal to Cj by G. So here F will be equal to Wp by G into Cj. If you can substitute that value, ISP will get in the terms of effective jet velocity and G. And the total impulse will be equal to ISP into WP. WP is the total weight of the propellant. So just remember this equation. This is actually important, this equation, and the second one, ISP is equal to Cj by G. Now the expression for specific propellant consumption. So specific propellant consumption means it is the weight of the propellant required for producing 1 Newton of power. So W dot P divided by F, or 1 by F by W dot P. So F by W dot P is IS. So SPC, specific propulsion consumption, will be equal to specific impulse, and the unit of this value will be, specific impulse will be in seconds. If you substitute the values, you can see. So unit will be in seconds, and so this SPC will be 1 by seconds. Now the propulsive efficiency terms, so three different efficiencies. So propulsive power, or the thrust power, the power which actually drives the vehicle in the forward direction, divided by the power produced by the engine. So F into U is the expression for thrust power. So m dot P into Cj is the F value, that into U will give the thrust power, divided by the kinetic energy losses of the exhaust gases. So kinetic energy losses means half into m dot P into Cj minus U all square. So this plus the propulsion power. So the engine actually produces power for driving the vehicle in the forward direction, plus this is actually power loss by the exhaust gases. So m dot P into Cj into U plus half into m dot P into Cj minus U all square will give the total engine output power. If you add these two values, so you'll get half into m dot P into Cj square plus U square, because 1 m dot P Cj U will get cancelled. So half into m dot P into Cj square plus U square. So kinetic energy loss in the exhaust gases will be equal to half into the final velocity minus initial velocity all square, and the rate of power loss will be equal to half into m dot P into Cj minus. So if you add these things, you will get the engine output power. Engine output will be equal to the propulsion power produced by the power loss. So propulsive efficiency will be equal to, so F into U by this value. So Cj into U, m dot P will get cancelled, half into Cj square plus U square. So if you divide with Cj, you will get this expression, efficiency, propulsive efficiency, as 2 sigma by 1 plus sigma square. So when sigma is equal to 1, or when U is equal to Cj, you will get eta P, that is a propulsive efficiency, as 100%. So this is actually the variation of propulsive efficiency with speed ratio. So when speed ratio is equal to 1, you will get the maximum propulsive efficiency. As U increases, obviously propulsive efficiency is going to be reduced. Now thermal efficiency is engine output power, the same expression what we have obtained previously. So half m dot P into Cj square plus U square divided by m dot P into Qr, that is the calorific value of the fuel, propellant is QR, that into m dot p is the total energy released by the burning of the fuel. So that is the thermal efficiency term. So Cj square plus U square by 2 into QR, and overall efficiency is the product of the thermal efficiency as well as propulsive efficiency. So the threads produced divided by input, how much power is given as an input. So the overall efficiency will be equal to eta P into eta Ti. So these are the fundamental terms associated with rocket propulsion. So just remember all these expressions because it is important for solving the problem.